Jupiter is 390 million miles away. Voyager 2 reached it in less than 2 years. With modern technology, we could get there in 2 to 3 years. It sounds almost doable. But getting to Jupiter isn't the main problem. The problem is that Jupiter doesn't want you there, and it has ways of making sure you never leave. I'm not talking about storms or cold or distance. I'm talking about something far worse. Something that would kill you before you even got close to its clouds. And the terrifying part, the closer you get, the faster it happens. Let's be straight about this. This isn't rhetoric. It isn't doomsaying. It's a cold, clear-eyed reading of what we know about physics, biology, and space engineering. Because Jupiter isn't dangerous the way a volcano or a storm is dangerous, something you can go around, wait out, survive with the right preparation. Jupiter is dangerous the way gravity is dangerous. Constant, impersonal, mathematically absolute. Anyone who went there with the technology we have today, or with any technology we can realistically expect to develop in the coming decades, would not be coming back. Not because of bad luck, not because of human error, because of physics. Let's start with a paradox that most people never stop to consider. Jupiter isn't as far away as Saturn. At an average distance of about 390 million miles from Earth, it's less than half the distance to Saturn. Voyager 2 launched in 1977 reached it in under 2 years. With an optimized direct trajectory, a modern spacecraft could reach Jupiter in 2 to 3 years. Compared to the eternity required to reach the outer planets, it almost seems within reach. And that's exactly what makes its proximity so deceptive. Jupiter doesn't kill you with distance, it kills you with everything else. Start with the journey itself. 2 to 3 years in interplanetary space are not 2 to 3 years on a cruise ship. The moment a spacecraft leaves Earth's magnetic field, astronauts enter an environment that is genuinely hostile to human biology. Galactic cosmic rays, ultra-high-energy particles fired from distant supernovae, traveling at a significant fraction of the speed of light, pass straight through the spacecraft's hull as if it weren't there. Solar particle events can flood the cabin with radiation in a matter of minutes. Astronauts on the International Space Station, shielded by Earth's magnetic field, absorb roughly 150 millisieverts of radiation per year, about 50 times more than the average person on Earth, but still manageable. In deep space, that number climbs to between 600 and 1,000 millisieverts per year. NASA's current career limit for astronauts is 1,000 millisieverts total. A single one-way trip to Jupiter would blow past that limit before you even arrived. But here's where Jupiter reveals its true character. Because the closer you get to the planet, the worse it gets. Much worse. Jupiter's magnetic field isn't just the most powerful in the solar system after the Sun's, it's almost incomprehensibly intense. 20,000 times stronger than Earth's. A magnetosphere so vast that if it were visible to the naked eye from Earth, it would appear larger than a full moon in our sky. And unlike Earth's magnetic shell, which protects us from radiation, Jupiter's magnetosphere is a particle accelerator. It captures electrons and ions, many of them blasted into space by Io, Jupiter's hyperactive volcanic moon, and whips them to velocities approaching the speed of light. What it creates around the planet is not a shield. It is a wall of death. Enjoy deep fact-check space stories? Hit subscribe and activate the notification bell. Otherwise, YouTube will not show you the next videos, and you'll miss what we uncover next. The numbers near Jupiter require a moment to truly sink in. At the distance from Jupiter corresponding to Io's orbit, the innermost of its large moons, about 262,000 miles from the planet, the radiation dose reaches 3,600 rem per day. For context, 100 rem received over a short period triggers the first symptoms of radiation sickness. A dose of 400 rem over a few days is lethal for roughly half of all exposed humans, even with medical care. Near Jupiter, you would hit that lethal threshold in just a few hours. The entire human organism would be destroyed within a single day. Even at what might seem like a safer distance, say at the orbit of Callisto, the outermost Galilean moon, about 1.2 miles from Jupiter, radiation levels remain orders of magnitude beyond any threshold the human body could tolerate over the timescale of emission. The Galileo probe experienced this firsthand. Designed for an extended mission around Jupiter between 1995 and 2003, it accumulated radiation damage progressively, and it was a machine with no organs, no DNA, no nervous system to protect. Its circuits degraded, image quality deteriorated, systems built to last failed ahead of schedule. By the end, it was a wounded machine dragging its remaining circuits through its final orbits. The same radiation that slowly wore down hardened electronics would have killed a human crew within days, and the obvious fix, adding more shielding, actually makes things worse at these energy levels. When ultra-high energy particles slam into dense material, they generate cascades of secondary radiation. The armor becomes part of the weapon. Now, let's set the radiation problem aside. Let's say some revolutionary technology, an active electromagnetic shield perhaps, or a particle deflection system that hasn't been invented yet, solves it completely. The fuel problem remains, and the rocket equation is just as merciless here as it is everywhere else in the universe. Reaching Jupiter requires enormous amounts of propellant, but the brutal logic of space travel means that every kilogram of fuel on board requires additional fuel to carry it, and that additional fuel requires even more to move itself. This compounding cycle, formalized in the Tsiolkovsky rocket equation, means that the ratio of fuel to payload doesn't grow linearly with distance and velocity. It explodes exponentially. The Cassini probe sent to Saturn weighed around 12,300 pounds and still needed 7 years of gravity assist maneuvers, swinging past Venus twice, Earth once, and Jupiter once to reach its destination. A crewed mission to Jupiter would need to carry life support systems, years' worth of food and water, radiation shielding, medical equipment, and spare parts for every conceivable failure. The mass climbs into the hundreds of thousands of kilograms. The fuel requirements become planetary. And then there is the gravity trap. This is Jupiter's most lethal mathematical secret. Earth's escape velocity, the speed required to break free of its gravitational pull, is about 25,000 miles per hour. That's already an enormous amount of energy to generate. Jupiter's escape velocity is about 133,000 miles per hour, more than 5 times Earth's. Jupiter is so massive and its gravity so relentless that just inserting into orbit around it requires shedding an enormous amount of velocity on arrival. And leaving? Leaving means accelerating the spacecraft back up to 133,000 miles per hour from whatever orbit it's in. For a crewed spacecraft carrying fuel and supplies for the return journey, the propellant mass required for that departure burn becomes so astronomically large that it overwhelms any conceivable rocket design. That return fuel would have to be carried from Earth because there's nothing at Jupiter to refuel with. All that fuel adds mass. More mass requires more fuel to move it. The cycle has no clean exit. Jupiter's gravity isn't just an obstacle to overcome on the way in. It is a cage whose bars are made of mathematics. It's worth pausing here to acknowledge something. Everything we've discussed so far assumes the goal is simply reaching the Jovian system and surviving the journey. We haven't even touched on what happens when you arrive, because Jupiter has no surface. There is no ground to land on, no solid place to set foot. Jupiter is a gas giant, a world of hydrogen and helium that grows denser and hotter the deeper you go, with pressure climbing to millions of atmospheres and temperatures reaching tens of thousands of degrees, until the hydrogen itself transitions into a state that behaves like liquid metal. Anything we could possibly build would be crushed and vaporized long before reaching anything resembling a bottom. You cannot land on Jupiter. You can only orbit it and deal with everything that orbital environment throws at you. The realistic scientific goal would be to study its moons. From a planetary science perspective, they are extraordinary. Europa may harbor a liquid water ocean beneath its icy shell, making it one of the most serious candidates for extraterrestrial life in the solar system. Ganymede is the largest moon in the solar system, bigger than Mercury, and has its own magnetic field. Callisto is an ancient, cratered world that preserves a record of the solar system's first billions of years. Scientifically, the Jovian system is irresistible. The problem is that studying it from orbit means staying immersed in that radiation environment for months or years. And every month spent within Jupiter's influence means more radiation damage, more biological degradation, more wear on onboard systems. And then there is the human body, which, in the absence of gravity, begins to dismantle itself with methodical indifference. Bones lose density at roughly 1 to 2% per month in microgravity, a rate that doesn't plateau after a few months, as was once hoped, but continues as long as the weightlessness does. After 2 to 3 years of transit in each direction, plus operational time in Jovian orbit, an astronaut would have lost 60, 70, 80% or more of their bone mass. Fractures from ordinary movements would become a real threat. The skeleton would be barely capable of supporting its own weight in any significant gravity. Muscles follow the same trajectory. The heart, also a muscle, shrinks as it adapts to the reduced workload of pumping blood without gravity's resistance. Cardiovascular capacity collapses. The eyes undergo changes as intracranial pressure increases with the fluid shifts of weightlessness. Vision problems already appear in ISS astronauts after missions measured in months. After years, permanent damage becomes near certain. The immune system weakens. Dormant viruses reactivate. Wound healing slows. By the time the human body reached Jupiter, it would already be a shadow of the one that left Earth. There's also a factor that rarely gets the attention it deserves: communication. At Jupiter's distance, a radio signal traveling at the speed of light takes between 35 and 52 minutes to cross the gap between the planet and Earth, depending on orbital geometry. A simple message saying, "We have a problem," takes 35 to 52 minutes to arrive. The reply takes just as long to come back. In any emergency, a medical crisis, a critical system failure, a collision with debris, the crew is alone. Completely, absolutely alone. There's no real-time guidance from mission control. There is no rescue mission that could be organized on any useful timescale. Every problem that comes up must be solved on board, with the resources on board, before it cascades into an unrecoverable failure. The psychological weight of that isolation is almost impossible to fully model. Human beings are social creatures, wired for connection, for the reassurance that somewhere, someone can reach you. At Jupiter, no one is coming. So, where does all of this leave us? Jupiter's not Saturn, it's closer, and in some ways that actually makes it more insidious: the illusion of accessibility. But the radiation environment around Jupiter is incomparably more lethal than Saturn's. Its gravity is the most extreme of any planet a human spacecraft might approach. Its moons, the real scientific targets, sit inside a radiation belt that would kill an unshielded human in hours. The fuel math for entering and escaping its gravitational grip is, with current propulsion, prohibitive for a crewed round trip. And the biological toll of the journey in both directions would come due long before the physics problems did. A human being who traveled to Jupiter would arrive as a radiation-damaged, physically compromised version of themselves, orbiting a world they could never touch, with no realistic path home. That isn't pessimism. It isn't a failure of imagination. It's a clear-eyed reading of the laws of nature, which have never once been talked out of their position by human ambition. Maybe future generations will find a way. Nuclear fusion propulsion could dramatically cut transit times, slashing radiation exposure and psychological damage. Advanced active shielding, magnetic fields generated by superconducting rings around the spacecraft, might deflect enough particles to make survival possible. Technologies we haven't imagined yet may crack problems that today seem absolute. There is a long human history of declaring things impossible and then doing them. But with everything we know today and everything we can reasonably project across the coming decades, Jupiter remains what it has always been: the king of the solar system, magnificent and merciless, sitting atop a gravitational and radiative hierarchy that has no interest whatsoever in human visitors. Some distances aren't measured in kilometers. They're measured in the gap between what we want and what the universe is willing to allow. Jupiter sits on the wrong side of that line, and it has no intention of moving. So what do you think? Did watching this video raise any doubts or questions? If so, please let us know in the comments. And if you thought Jupiter was impossible, Wait until you see what Saturn has in store. Watch why anyone who goes to Saturn will never come back, to discover why the ring giant might be even more terrifying. Click the link on the screen.